right, so section 7.3, we're going to look at solving trig equations graphically. And you might think, well, yeah, we did that yesterday with simple problems like that. So we're going to look at a kind of a simple one again. But then we're going to get into trig equations that have higher powers in them, like cosine squared, sine cubed, things like that. And what's really important when you're writing answers to these kinds of problems is you're going to have to put plus the period times n on all your answers. But we've never talked about the period of something squared or something cubed. So we got to figure out a pattern for finding the period of not only a trig function, but a trig function to a power. So the 2 pi over b and the pi over b formulas we talked about yesterday, that's all we need to know. Those are going to work. But I need to show you how. All right. So this is kind of a review of what we've done before. But remember, if they ask you to find all solutions to a trig equation, like they did last night in the homework, the first thing is you graph it on the calculator, you set your window to 1 cycle, and you find all the solutions that are in 1 cycle. Then you have to add something onto the end of all of them, because that solution is going to repeat itself every cycle. So we take that into account by putting the plus pi n or 2 pi n. Those are the most common ones, but we need to put plus the period times n to take into account the fact that the answers are going to repeat. That's what a periodic function is. It repeats itself. So if you get one answer to a periodic equation, you really have infinite n. Okay, that's the first step, and the calculator is going to help us with this step today. Eventually, I think in section 7.6, we're going to solve trig equations and inequalities algebraically. When we try to solve it algebraically, something special has to happen because trig equations can be pretty hard to solve if things don't cancel out or something doesn't happen that's nice. When we're graphing them, we could get any kind of answer. It doesn't matter if it comes out nice or not, because all we really have to do is find an intersection point. We don't have to do a lot of algebra. So let's try this one. Sine of x equals 0.8. And the first thing you need to write down is the period. What's the formula for the period of the sine function?
2 pi over b.
It's 2 pi over b. And what's b in this case?
1.
1, because there's a 1 in front of the x. So that 2 pi tells me what to set my window to. I want to set a window from 0 to 2 pi. So if you want to get that first, you can set that up. And what would I put in y1? Sine of x. And y2? 0.8. I already did my window. I didn't check the range. I was just checking it. The range is fine. I'm in radians. So hit graph. If you're doing this in degrees, you wouldn't want to set a period length of 2 pi. You'd want to do 0 to 360. Okay. So it does say to find all solutions. So right away, that means you're going to be putting a what on the end of each answer. Yeah.
So plus 2 pi n.
Right. So we can set that up right now so it's ready to go. That's what your answers are going to look like. And why did I put down 2 of them?
Because there's 2 points on this side.
Yeah, there's 2 points where the 0.8 equals the sine of x. Those 2 points are evenly distributed around the maximum that occurs in the first half of that cycle. So if you knew where the maximum was and you knew one of them, well, the other one is the same distance on the other side. Okay. But I'm not going to find the maximum. I'm just going to do an intersect. So I get 2.21. Second calc intersect. This time you do need to move your cursor to the left of the maximum. And you get 0.93. If they don't say where to round, I would say 2 decimal places is usually pretty good. Any questions on that one? Okay. So if we take a trig function, instead of setting it equal to 0.8 like we did in the last one, let's say we set it equal to 0. You're still solving for the answers, but now the answers have a special name. Does anybody remember what you call the answers to an equation? That when you plug them in, you get 0.
Oh, is that, I think I do.
Roots.
Yes, I just had it.
So if you set the equation equal to 0, and you solve it, then you're finding the roots of the equation. In the last problem, we didn't really find roots. We found numbers that give you 0.8 when you plug them in, not 0. But setting it equal to 0 would be to solve for the roots. So if you see an equation that says solve the following for the roots, that means set it equal to 0. Any question on that? That's a lot of what we're going to focus on when we do some equations coming up, setting them equal to 0. And the reason why we usually set it equal to 0 is because when we start solving these things algebraically, setting something equal to 0 is usually what you have to do. Like if you want to use quadratic formula on something, you get it equal to 0. And you can actually use quadratic formula on trig equations. So we're not going to do that today, but we'll get to that. So let's say we set some equation equal to 0, and we get n solutions. So in the last problem we did, we had 2. These represent all of the solutions within one cycle, or one period. If you want to represent all the solutions in general, not just within one period, you have to put what on the end of each solution? Right. You can't just say put 2 pi n or pi n. We don't know that. All we know is you need to put plus the period times n on the first solution, on the second one, the third one, fourth one, fifth one, however many you have.
What's the NE's thing? This side there. What's that mean?
So what does that mean? Okay, well, what does this mean? Remember? We talked about that symbol probably way back. Maybe the first day. Is it the what symbol?
Real number?
It's not the real number symbol. Real number symbol, I think they usually do something like that. That's the real number symbol. Yeah. Integer. So this means integer. This symbol like this looks kind of like an E, means an element of. So that means that this letter is an element of the integers, or this means it has to be an integer. So remember, this is always an integer. You can add integer multiples of your period to an answer to get the next answer. You can't add half a period. No, answers don't usually occur half a period later. They occur one full period later, or one full period earlier. But it has to be a full integer period. Okay, so nothing new here. That we just did that in the last problem. You may get more than 2 solutions, and it's like, I don't think we've had one yet, but we're definitely going to have one today. So, how do you find the period of something that has multiple trig functions in it? Don't even worry about the power here. But how do you find the period of each of that whole thing? Well, the first step is to find the period of each periodic term. How many terms are on the left side of that equation? 3. 1, 2, 3. Terms are separated by addition and subtraction signs. How many of those terms are periodic? 2. The plus 1 is what you call a constant term. That's not periodic. But anything with a trig function is periodic. So what we have to do is find the period of cosine squared, and then find the period of sine. So the first step is to find the period of each individual periodic term. How are we going to figure out the period of cosine squared? Well, don't worry about that yet. We'll figure that out. Once you know the period of each individual term, the period of the entire equation is the least common multiple of those periods. So to use kind of simple numbers without pi, most of the time period is going to have pi in it. But let's say one of them had a period of 2 and the other one had a period of 3. The period of the whole thing is 6 because it's the least common multiple of 2 and 3.
What's Al's?
So the way we're going to figure out the period of a trig function to a higher power, at least for the first problem, is we're just going to graph it, and we're going to look at it. We're going to set a window, and we're going to see if we can figure it out based on the window. Once we figure it out the first time, we're going to try to come up with a rule for figuring it out. And it really has to do with whether you raise a trig function to an even power or an odd power. That controls the period, along with the type of trig function. Sine, cosine, tangent, things like that. All right, so let's look at this. Well, we should be able to get the period for sine. What's the period of sine?
2 pi.
2 pi. So remember, the least common multiple cannot be any smaller than the individual periods. So the least period of this entire thing is going to be at least 2 pi. It has to be. Now we need the period of cosine squared. 2 does not affect the period. That's a vertical stretch. If you had a number next to the t, that would be a horizontal stretch or compression. Yes, that would affect the period. But this 2 doesn't. So don't worry about the 2 for right now. Let's just put in cosine squared. And this is how you write cosine squared on paper. That's what it looks like. What it really means is this. That's how you have to do it on the calculator. It's just a notation that they use. That's pretty much a notation you can only do on paper because you can't type it in on the calculator like that. So let's put in cosine x, and it is important you close the parenthesis. Otherwise, you're going to be taking x squared and then the cosine of that. We want the cosine of x, and then square the answer after. Okay, let's set a window from, let's just leave it like that, 0 to 2 pi. And I'm going to graph it. So we know what we set the window to. How many times does it look like cosine squared is repeating? Twice. We're getting 2 cycles. There's 1. There's 2. So if we're seeing 2 cycles from 0 to 2 pi, then how long is 1 cycle? And that's what I'm going to put here. Pi. Yeah. So the period of cosine squared is pi. Now that we know the period of each individual term, the period of the entire equation is the least common multiple of 2 pi and pi. 2 pi. Yep. So we're going to write that down. So the period is 2 pi. So when we're talking about what do we put on the end of each answer, that's what it is. It's a plus 2 pi in this case. 2 pi. Okay, so now we need to put in the rest of it and graph the whole thing. So let's put in 2 cosine squared x plus sine x plus 1. And you're not going to be calculating an intercept. What are we calculating this time? The root. Now, my window's a little bit, I mean, it's fine to calculate the root because I can see where it crosses the axis. I just can't see the very top of it, but it doesn't really do anything special. It just curves right back down. But that's what one cycle of this trig function looks like. It's not quite a wave, the way we're used to seeing a nice kind of symmetrical pattern, because we've complicated it a little bit. This is the pattern that we keep repeating. Just like that. So the next section, if you set your window to 4 pi, this is what you would see. Just like that. And you keep pasting that section all the way down. That's the pattern for this one. Okay, so that's 2 cycles. Okay, so we got to figure out how many times it crosses the x-axis. How many times does it look like it crosses? Once. I'm going to zoom in just to check it. There's no question that it doesn't cross in any other spot other than pretty close to where I just put my cursor. So let's zoom in there and see if it goes below and then back up. I think it just comes down and touches it and then bounces off it.
Hard to see.
Yeah, there's a tick mark right there. I think it could zoom in one more time. But if it's still hard to see when you zoom in again, then it's probably not crossing it twice. Okay, because we're zoomed in really far now.
It's kind of hard to tell.
Yeah, it's still really hard to tell. So what we're going to do is let's do second calc 0. And what we can do is watch the y value. And we can see that it's positive. And as I go to the right, all of a sudden it just went pretty close to 0. That's like 0.0005.
Sorry, where was it?
And then it hits 0. It never went negative. It kept getting really, really close. But as I traced it, it never went to a negative number. Which means it's only going to cross the x. It's just going to touch the x-axis and bounce up. Another way is, if I find the 0 in this area, and it's exactly in the middle, then I know that's probably only 1. Because if there were 2, they would be off to the sides a little bit. You know what I mean? When you look at them. And it's probably going to be right in the middle. It's exactly in the middle. So there's no way that it crosses more than this. So it crosses at about 4.71. Okay, so x is about 4.71. And what do we put on the end of that? Plus 2 pi n. Remember, you don't need to put minus because n is an integer. And if it was negative, then it would make 2 pi negative, which would be like subtracting. So there's your answer. So you're going to get an answer starting at 4.71 and then repeating every 2 pi units left and right. let's look at this one. I don't think I need to go into the chart yet about even and odd powers, because these are just to the first power. So we should be able to get these. But I want to solve it like I did the last one. So what do I want to get it equal to first? Yep. I think the easiest way is just to go like this. Okay. What's the period of the first periodic term? 3 cosine x. 2 pi. What's the period of tan x?
Oh, that's pi.
Just pi. What's the least common multiple of those?
Pi again.
2 pi again. 2 pi comes up a lot. Okay, so now we know what we're putting on the end of each answer. We know what we need to set our window to. All right, so type it in. Let's do 3 cosine x minus tan x. I'm going to reset it because I did a lot of zooming in that last problem. So I'm going to do zoom 7 just to put it back the way it was. And I can stop it if I want. I just want it to reset the window. And now I'm going to set it to what I want. So I need to go how wide of a window?
2 pi.
0 to 2 pi. Yep. You need to find all the answers in one cycle.
Yo, mine's back there. Matt.
And that's the pattern that we keep repeating over and over. So copy and paste that right here. This section should always join up with the section you started with because they're really the same thing. If they don't join up, could mean something wrong. Okay, how many answers do we get per cycle here?
2.
2. So let's get that ready. Plus 2 pi n. Plus 2 pi n. Okay, I'll go ahead and find the one that's further to the left. If someone else can find the one that's a little bit more to the right,
Alright.
that would be helpful. Count 0. No zooming required here. It's pretty clear. It's 2 answers. Okay, so your first one is 1.01. And your second one is
2.13.
2.13. There you go. Plus 2 pi n on each of those.
Yes, sorry. Yeah. I assumed it was in college.
Any questions on that? Okay. All right, well now we're getting into one that's cubed. All right, so rather than playing around with like graphing it and trying to figure it out, I'm going to show you a table for figuring out the period of a trig function raised to a power. Because not only is this one cubed, but we're also doing a horizontal stretch or compression to it. In this case, that's a horizontal.
That's this shit. No, that's stretch. That's what I meant.
It's a shrink. It's a compression.
Yeah.
The bigger you make this number, the more that it shrinks. So we're cubing it and shrinking it. So there's a couple things happening. So that kind of complicates what the period could be. So here's a summary of the periods for all the trig functions. The formula I'm about to give you works all the time for tangent and cotangent. It doesn't matter whether it's even or odd.
So this isn't the formula, right? It's just.
This is going to be the formula to do this problem. So you might want to leave some space to do this problem. I would say as much space as you left to do this one. And we could put the table, however you want to put it. But this is going to be the formula if you have sine, cosine, secant or cosecant to an even power, or any tangent or cotangent. Now, because of this at the end, because the formula works for any tangent or cotangent, you already know the formula for tangent. What's the formula to find the period for tangent? Pi over b. And if you think of tangent, what power is really in that problem, even though it's not written?
1.
Yeah, so this is the formula for tangent to an odd power, pi over b. Well, if I'm saying that that's the formula for tangent to an odd power, or an even power, or any of these, then all of these are going to use the formula pi over b. I don't think b is ever going to be a negative, but remember, period is the length of the cycle. You shouldn't have a negative cycle length. So that's the formula that you use in any of those cases. Now, the other cases you could have would be sine, cosine, secant, or cosecant to a odd power. And the formula for that
What's T stand for that?
is 2 pi over b. T is the period. That's usually the letter they use for period. I don't know why. So you might have a different way you can organize that to make it shorter, but that's when you use each formula. So use pi over b if you have any of the top cases. Use 2 pi over b for any of the bottom cases. So now we don't have to kind of guess what the period is. We've got an exact way to figure it out. Even if you have a number in front of x, this formula takes that into account as well. Okay, so we'll go back now and look at the problem we were doing, which was, I think, a sine cubed, and see if we can figure out the period. What's the formula that you would use for sine cubed? 2 pi or pi? 2 pi.
Wait, what?
Why?
Because it's up.
Because it's odd.
said use a cube.
What's the b value in this case? 2. So that's the formula you use to find the period of sine cubed 2x. So what's the period? Pi. What's the period of 2 cosine x? 2 pi. What's the least common multiple? Yep. Again, it does not always have to be 2 pi, but in a lot of the examples that does come up a lot. Any question on the period? Okay, now I need to type all that in. So we have 3 sine cubed 2x. Remember, you're not cubing the 3 in the front. You don't want it to say 27. So be careful when you use your parentheses. So we're going to do 3 parentheses sine of x. Close the parenthesis for that.
Maybe 2x.
Yeah, sorry, 2x. I don't even know if I need that extra parenthesis. Can't hurt it. So that's going to just cube the sine 2x. It is not cubing the 3 because it's outside the parentheses. And then minus 2 cosine x. Okay, you need a window from 0 to 2 pi. We already have it. And we're looking for how many times this crosses the x-axis.
Should be 6 as well.
How many times?
6.
Yeah, 6 times.
That's a lot of solutions.
Yeah, we're not going to go through and do each one. I already have them done. You just have to find all the intersects. Or not intersects, roots. So it comes out to 0.5, 1.25, 1.57, 1.89, so there's kind of a cluster of them, 3 of them that are all pretty close together. Then the next one's a little bit further, 2.65, and then the next one's even further, 4.71. And each one of those would have a what on the end of that?
Plus 2 pi n.
Yep. So they all have the plus 2 pi. Nothing hard about this one, it's just more time consuming to find all those
You
answers.
have that many
Yep.
solutions. Or
And notice here the beginning would meet up with the end, if you kind of wrapped it around. Nothing interesting happens where it goes off the screen. It's not really important because we're not looking for maximums, but it basically does that. Any question on how we found the periods or those 6 answers? So we just did the summary. All right. So some inequalities. So inequalities, solving them, it's just like solving equations. The only difference is when you write your answer, it's usually not x equals a number. How do we usually write an answer when there's an inequality involved?
Less than or greater than or
You can use inequality notation, or you can also use interval notation. Sometimes there's a union, like in this last problem, if you wanted to know where the graph is below 0. Let's say this was a less than 0 problem, not equals. Well, less than 0, I would find these 2 roots and say between those 2, I would say between those 2, and then I would say from here up to, but not including the end, because usually when you set a window, if you include the left side, you don't include the right side, because they're the same thing.
oh, I see.
So there would be 3 sections here that are below 0. 1. Oh, yeah, sorry, I missed that one. This you can include up to there. So there'd be 1, 2, 3, 4 sections that are below 0. That's usually more than we have. That's a pretty complicated one. Okay, so first you still have to find all your roots, but then you have to take into account whether you want to be above or below the axis. Make sure you either use brackets or parentheses. You never use a bracket on the right edge of the screen. We always use a parenthesis unless they change the directions. If you have asymptotes in a problem, you can't include those. There were no asymptotes, I don't think. Where's the graph? Oh. Yeah, there's no asymptotes in that last problem because you were only dealing with sines and cosines. When you throw a tangent or a cotangent or a secant or cosecant into the problem, then you're going to get asymptotes. So then you got to be careful. Pretty much just if there's a vertical asymptote, it's going to be easy to find. It's going to be like right in the middle of the screen. So like if you have 0 to 2 pi, it'll be a pi. Right? It's not going to be a hard asymptote to find because that could be pretty tricky with a trig equation. Bless you. Especially when you start cubing it, squaring it, it could get a little tricky to figure it out. So asymptotes are not going to be overly complicated. Keep in mind, yeah, vertical asymptotes. Always, if you have a vertical asymptote in the problem, that breaks your interval. You can't continue through an asymptote. You have to stop your interval there with a parenthesis. And I think we're going to have one with tangent or cotangent. So, okay. So the first thing we want to do is get what number by itself on the side.
0.
What's one way I can do that?
Subtract sin x from both sides.
Okay, so we could subtract sine x from both sides. Okay, now, are we going to have asymptotes in this problem? Yes, so we're going to have a graph that doesn't connect.
How can you tell?
Because I have a cotangent.
Oh,
Cotangent is a discontinuous graph.
yeah, that's right.
Now, before I actually put this in, I should find my period. What's the period of cotangent to an odd power? With a 1 in front.
Cotangent to an odd power is even or odd, right? They're both.
Yeah, it's the same formula. Pi.
Oh, I'm.
What's the period of sine x? And the least common multiple? 2 pi. Okay, so we know what to set our window to. That should already be set up. How am I going to type in cotangent? Yeah, that's one way. Or if you wanted, you could also do, you could do cosine divided by sine. Do the same thing. Okay, so just make sure we get that typed in right. Make sure we got our window 0 to 2 pi. And we are looking for where it is less than 0. Now, it might look like those are just the same curve twice, but can everyone see the curve is a little different?
It's like flip.
Yeah, it's like this is like concave up, and then this section is concave down.
The same line of flip.
All right, so we want to figure out where it's below the axis. Not equal, strictly below. And we're going to find all solutions in the window from 0 to 2 pi. That's the window we just set based on this number. How many sections are below the x-axis? 2. This one. Oh, don't include it. And this one.
Oh, yeah, this stuff is equal.
So I need to figure those out. I need to know what those values are. But let's at least set up our brackets and parentheses. For this, let's call this interval 1, and this curve over here will be part of interval 2. For interval 1, do I include or not include the left edge?
No.
Not include because of this open circle.
Because, yeah.
How about the right edge? Include or not include? Not include because what's happening there?
It's going to be infinity.
There's an asymptote. So that section is approaching something and stopping. That asymptote is exactly in the middle of the screen. And that goes from 0 to 2 pi, the screen. So where do you think the asymptote is?
Pi.
Pi. And you can verify that by going to the table, type in pi. Well, if you can type it in, you will get an error. You get an error. So pi is the asymptote. So include pi or don't include pi? Don't include it. Now the next section starts where that circle is. Include or not include? Don't include. And we know it's going to end at the right edge of the screen. Do I include or not include the right edge?
Not include.
Yeah, you don't include it because if you include the left, which is 0, you don't include 2 pi because they're the same thing. 0 and 2 pi are equal. So not included. So the only thing left to do is find the roots for those two values. Is there any question on how to find those?
It's just the.
Yeah, we'll just call this root 1 and whatever root 2 is. So this is root 1 and this is root 2.
So you could go to 0 for that, or just put a line at 0 and find the intersect.
You could put a line at 0 and then do an intersect. I would do the root, but yeah, you could.
That's what I've been doing because it says that 0 is less than, so I just put 0 on line 2. And
Yep.
just kind of keep it there so that you can just intersect instead.
You could do an intersect. Yeah. But any questions on answer to that one? Okay.
It was open. There wasn't any brackets in that last one.
There were no brackets. Nope. All right, let's do this one. And it says to graph it as is. So don't get it equal to 0. Just put what's on the left in y1. Put what's on the right in y2. Now, what's on the left is sine 2x. Is that periodic or not periodic?
That's going to be a shrunken sign.
So is sine periodic or no?
Yes.
Yes.
Yeah, it repeats.
How about x squared minus 1? What's that?
That's a parabola.
It's a parabola. A parabola is periodic.
No.
No.
That's just one.
There's just one of them. It's not like the parabola keeps repeating itself. So when we graph this one, we are not going to have an infinite amount of intervals. It's actually what I should have done. I forgot on this one. Is each interval, you should put plus 2 pi n.
No, you can't do it this way.
Because, I'm sorry, I forgot the plus 2 pi n. Because these two answers are going to repeat the next cycle over and the cycle before. So there's an infinite amount of these sections that are going to be below the x-axis. Yep.
And that plus pi n, that would go right after each parenthesis. Like each.
The plus 2 pi n, yeah, technically, if I wanted to write it really nice, it goes on the first number, the second number, the third, and the fourth.
Whoa.
You can add 2 pi n to all those values and shift everything to another cycle.
Dang. Or you could put it outside the parentheses.
Yeah, I understand what you mean if you do it that way. That's fine. But on this one, it's not going to work that way. You're not going to be able to shift your interval and get more answers because the parabola is only going to occur one time. So let's do zoom 7. So there's my sine function. And I'm looking for where the sine function is above the parabola. How many spots is the sine function above the parabola?
2. I'll have one little segment with 2 intersections.
So can I describe where it's above in one interval, or do I need 2?
You need 2. Right? Oh no, that's my bad. This one.
Yeah, to me it looks like it's only above from here to here.
So
That's one. I never had to lift my pencil to draw that. So if I don't lift my pencil, then it's one section. Out here, all this stuff doesn't matter. That's all below the parabola. Think about it. Parabola would be, it's way, way up at that point. And same thing over here. It just keeps going up. So all this stuff is below. This is the only section where it's above. And it's said above or equal, which is why I use closed circles. So what kind of symbols would I use for closed circles?
Greater than or greater than or equal to.
Well, we're going to write an interval.
Bracket.
Bracket.
I'm sorry.
And it's just going to be from the first intersection to the second one. So you just have to find, this time, the 2 intersections, not the 0. So 0.46.
It's not negative.
Oh yeah, thank you. So negative 0.46. It does say negative, I just didn't look at it. Up to positive, might be symmetrical, might be 0.46. No, it's not. So don't assume that. 1.26. That's the interval where it's above the parabola. And that's it. Don't put a plus 2 pi n on that. The only way you could put a plus 2 pi n is if your parabola did this. And it kept repeating, so you could keep getting that same section all the way down. But that doesn't happen. Any question on that? Okay. This one, I'm just going to graph it. I'm not going to get into it too much right now. I just want you to see what it looks like. But I want to see where sine 1 over x crosses the x-axis. And again, I'm not going to get into it too much right now. Why? Let's do zoom 7. So, how many times does it look like it crosses the x-axis?
A lot. 4 at least.
5?
4 or 5. I can't tell if that's an asymptote in the middle.
If you zoom in, there's a lot more.
Well, let's set the window from -1 to 1, so we can zoom in a little bit and see what that looks like.
Oh my god.
That didn't help.
I'm assuming that if you zoom more, it'll probably cross more times.
Yeah, if you zoom in more.
Oh, infinitely, yeah.
Oh, wow. This, okay,
It
hold
just
on.
keeps multiplying.
There's a lot.
Yeah,
You
there's a
don't
lot.
say.
There's an infinite amount of answers to this problem. So there are some trig functions that, when you try to find the roots, not only are there an infinite amount of answers because you can do plus 2 pi n, without even doing plus 2 pi n here, because this type of function is not periodic. It's sine, but it doesn't keep repeating itself like a wave. So it's not really periodic. But there are an infinite amount of answers to where it crosses the x-axis.
Coloring in your screen at this point.
But it's just
Sounds like a lot, too.
And they-
-1 and 1, right?
All the answers, yeah, they do definitely occur between -1 and 1. But yeah, there are an infinite amount of answers to this problem. Okay. So I'm just not going to get into why right now, but I want you to understand some trig functions have an infinite amount of answers without even doing the plus 2 pi. So kind of an
So for that, we just put infinitely many solutions? Or?
yeah, you could put infinite, yeah, that there would be infinitely many roots to this problem. Yeah. And the last one we're going to look at is a double inequality. And to do a double inequality, you need y1, y2, and y3. You have a left, middle, and a right. So you graph the left, the middle, and the right all on the same axes. And then you just have to interpret what you're looking for. You might have to be below one of them, but above the other one. So a lot of times a double inequality is where you're sandwiched between two things. Not just under one thing, but under one thing and above another. Okay, so between. Alright, so we're going to look at this one.
Sorry, what was the second step?
We're just going to graph it
Alright,
on the calculator and then look at where we need to be above or below something. So we're going to graph negative x and positive x. Those are going to be my left and my right. Now, negative x and positive x, those are lines with a slope of -1 and 1. So we're going to get kind of an x shape. And we basically are going to want to figure out where this graph is going to be sandwiched in part of the x shape. Okay, kind of like in this section and this section. We're going to be let's see, this graph has to be, whatever graph we draw has to be under the positively sloped line. So we have to be under that. and we have to be above the negatively sloped line. So we want to be above that. So under that one and above that one.
So the right one.
Yeah, so I think that means it's going to end up being in the right section. I can see it better when I do it. And I do it in color, so it's easier to see. Now, this is a number, or it's not a number, but it's something in front of a trig function. When you put something in front, what kind of transformation is that?
Vertical stretch.
It's a vertical stretch. And x is not a number. What do we call x?
Variable.
It's a variable. So this is a variable vertical stretch, meaning the further away you go on the x-axis, the bigger the stretch gets. As you go towards the origin, the stretch gets smaller. So it's a variable vertical stretch. Let's graph it and see what it looks like. So let's do negative x. Let's do positive x. And then let's do x sine x. So negative x is blue.
You have to change the window.
And I gotta change my window. Negative x is blue, positive x is red. So negative x is blue, positive x is red, and x sine x will be the one in black. So we're looking for where the black graph is between the blue and the red. Okay, so let's see. Let's do zoom 7. There's your negative x. There's your positive x. And there's your variable vertical stretch, which you can't see that well. So let's zoom out. Negative x, positive x. It's basically
That's cool.
So sad.
it's staying within those bounds.
That's really cool.
So where is the black graph above the blue one and under the red one? Where does that happen? Above the blue, below the red.
X is greater than 0.
Anytime x is greater than or equal to 0.
That's just the answer.
Anytime that you are to the right, you're going to be above the blue and under the red. Any question on that one? Now, kind of a similar looking graph, but a little bit different.
Oh, no, okay.
What does absolute value of x look like? It's a V shape, and then putting a negative in front does what to it? It flips it, so we're going to get an upside down V shape. And this is where the color kind of comes in handy. So let's take and make this first one absolute value. I guess I just have to type it again. And make the second one absolute value.
You put the negative inside.
Yeah, was it outside? Okay, so yeah, that's not what you want. So notice in the graph we just did, it's not really a V shape in the top. The only reason it looks like a V shape is because it's two different lines crossing to make a V shape. But this V is not one equation. It's two different ones. Now compare that to this one. This time the V's are all one thing because you can see the V is the same color. And now they want to know where you are, let's see, above the blue one and below the red one, or equal. Where are you above or equal to the blue one and less than the red one?
It's not every time.
Yeah, that's all real numbers. You are always above the blue one and below the red one. So it looks like exactly the same graph, and if you did it in black and white, it wouldn't look any different than this one. But it is a slightly different picture. Questions on that? Okay, so that's 7.3. Okay, so solving more complicated trig functions graph. Okay, so homework, just keep in mind there's a couple sections there that are just odds. So 5 to 7, 11 to 15, that's all. 19 to 25 is odd. 29 to 31, that's just all three of them. And 33 to 37 is odd. Okay, so we will look at that tomorrow. And remember, we do not have a test tomorrow.
Yeah, no study. Well, I think it's no study.
So yes, you're nothing to study for this test this week, but you will see some of this next week.
I should prefer that for that.